Hello again, Algebra 2 class. This video set is on Chapter 9, Lesson 2 from your Algebra 2 textbook. That lesson is on series, which are very closely related to sequences. We have three main objectives today: evaluate series by expanding, evaluate series using formulas, and write series in summation notation. In this first video, we'll be evaluating series by expanding them. But before we do that, we probably want to define what a series is. Remember from our last video set, a sequence is just a list of numbers. Well, a series is just the sum of some or all of those terms that are in that sequence. So, for example, if we had a sequence 2, 4, 6, 8, the related series would just be 2 plus 4 plus 6 plus 8. Right? We're finding a summation instead of just a list. Now, many sequences go on forever and ever. There's not a last term, they just keep going. So a lot of the time, we are often interested in only adding up some of the terms in it. This is called a partial sum, and we write it as S sub n. S sub n is just the sum of the first n terms of a sequence. So like S sub 5 would mean the sum of the first 5 terms. Let's look at an example. Given the sequence below, find S sub 3 and find S sub 5. Well, S sub 3 is just the sum of the first 3 terms. So that's 1 plus 4 plus 7, which we can quickly do that math out, and you get 12. So the partial sum S sub 3 is 12. We can also find S sub 5 like they asked. That would be 1 plus 4 plus 7 plus 10 plus 13, right? The first 5 terms. And we can do that math out relatively quickly too. We got 5, 12, 22, 35. Now, as you can probably imagine, if you have a very long series with a lot of terms that have to be added together, that can take a while, and it's not a very convenient way to express that summation. There's a much shorter and more compact way to write it called summation notation, which can be seen here on the screen. So there are several pieces to this to point out. The first one is this strange looking symbol. That's actually the Greek letter sigma. It just means find the sum of all of these things. And there are a couple other things to point out, right? The summation notation will also tell us the starting term. So we're starting with the first value of k equals 1. It will tell us the ending term. In this case, we're ending with the 5th term. And it will give us an explicit formula for finding each term. So in this case, the rule that they give us to find the first, second, third, fourth, and 5th term is just 2 times whatever k is. Okay, so what does it actually look like? What that means we have to do here, if we want to expand this, is we would have to go ahead and to find the first term that we're adding up, we would have to plug in 1 for k. So we have 2 times 1. To find the second term, we would plug in 2 for k. So we have 2 times 2. And we'd keep going, 2 times 3, plus 2 times 4, plus 2 times 5. But we're going to stop at 5 because that is our ending value for k. Well, we can do a little bit of arithmetic here. We get 2 plus 4 plus 6 plus 8 plus 10. And now we have expanded our series. So let's look at a couple more examples. This first example here asks us to expand the series and then also evaluate it. All that extra piece there that evaluate means is once you've expanded it, actually add all those terms up and get a final number. So in this case, what we're going to have to do, we're starting with our first term when k is 1, ending with k equals 4, and this is our explicit formula, 10 minus k squared. So we can go ahead and plug in k equals 1 first, so 10 minus 1 squared, and then plus 10 minus 2 squared, plus 10 minus 3 squared, plus our last one, 10 minus 4 squared. And just barely fit. So we can do this math out. 1 squared is 1. 10 minus 1 is 9. Plus 4 squared is, 2 squared is 4. 10 minus 4 is 6. 3 squared is 9. 10 minus 9 is 1. And then finally we're adding on 4 squared is 16. 10 minus 16 is actually negative 6. That's okay, we're allowed to have negative terms in our series. And if we add all of these together, 9 plus 6 is 15, plus 1 is 16, plus negative 6 is 10. So this series evaluates to 10. Now, last example, one important thing to point out here, our starting value is no longer 1. It's actually 3. And which means in this case we're going from the third term of this sequence to the sixth term. We're not starting with k equals 1. So first we'll plug in k equals 3. 2 to the third power plus 2 to the fourth power plus 2 to the fifth power plus 2 to the sixth power, and that's our last term because that's our ending value for k. We can evaluate this. 2 cubed is 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64, and finally we can add all of those up, and I believe we get 120 for our final evaluation.